Today is a historic day in your journey of becoming quantum information scientists. Today is the day that you meet the density matrix for the first time. And not only do you meet the density matrix, but you also meet the partial trace, something we hold very near and dear to our hearts in quantum information. So we're in chapter 2.4, the density operator. Operators for us are always going to be matrices once we choose a basis. And imagine the following. We have a quantum computer, and we have a quantum state psi. But the quantum computer is not perfect, as they are, unfortunately. So let's say there's some probability that a bit is going to flip. So with probability p, let's say I get a bit flip error, poly x. And with corresponding probability 1 minus p, I remain in the state psi that I had. So generally, let's think about this as with some probability p1, I have a state psi 1. And with some probability p2, I have a state psi 2. And you can imagine, this is general, so this could go up to pn psi n. In a way, because we have errors that can happen in our quantum computer and our quantum states, this is going to be the most general way that we're going to describe a quantum state. So it's not just a single wave function. It's a collection, or what we'll call an ensemble of wave functions, where the p's form a probability distribution. Okay? So here in this case, there are two options. P plus 1 minus p will, of course, be 1. And in the general case, with n wave functions, we want the sum over the p's to be 1, so it defines a valid probability distribution. Now we have to think, how are we going to work with this ensemble of wave functions? At this point, hopefully you're very good with working with one wave function. Now we have to think about this. Let's suppose that we want to compute an expectation value with respect to this ensemble. So let me have some operator. I used x in my notes for whatever reason, so I'll use that here. It could be poly x, or it could be general. So let's see what this would be. Well, hopefully you can reason from the definition of an expectation value that this would just be the probability p1 times the expectation value with respect to psi 1, and so on all the way up to pn times the expectation value with respect to psi n. This is just the linearity property of the expectation value. And let's write this as a summation, sum over I going from 1 to n of pi psi I, whatever the operator x is, psi I. And now I'm going to do the following thing. You remember from last time our rule that for any expectation value, which looks like this, I can rewrite it in terms of the trace. You remember this? So let me rewrite this, still using the summation over I, going from 1 to n of pi. And then I'm going to use our rule from last time that this can be written as the trace of x times the outer product psi I, psi I. If you don't remember this, look back in your notes. This is one of the most useful things for us to know in quantum information. We can write an inner product, this expectation value, with the trace. And now we know that the trace is a linear operator. So that means I can put the summation over pi inside of this. So let me do the following. Let me write this as the trace of the operator x, doesn't depend on the index I, and then I'll put in parentheses this sum over I, going from 1 to n, of pi times psi I outer product psi I. This object that you see in parentheses pops up here and in other places, and it's a very useful thing for us to work with, so useful that we give it its own name. This is exactly the density operator, or I'll write the density matrix. And almost always we'll use a Greek letter to indicate this, usually starting with rho. And then if we have multiple, we'll use a sigma and a tau. But usually you'll see the density matrix written as rho. This is what we're going to use to sort of compactly describe our ensemble of quantum states, which is the most general thing that we can have in a quantum computer, in a quantum system.